Hello, students. This is Professor Sean McMahon, and I'm going to be covering lectures for a general chemistry semester one course. The book that I use typically is TRO, which is the third edition, and that's where I pretty much get the PowerPoints for these presentations and lectures that will follow. In every single lecture, I'd recommend not only having scratch paper to work with, a pen to write with, I'd recommend having a calculator and a periodic table out every single time. It just makes your life so much easier, and you can participate with these pre-recorded lectures in real time. For the majority of these lectures, I'm not going to show myself, so I'm going to go ahead and turn off this video just to let you know that's not my real background. I wish I was on the beach. I just had that because I love living in California, but I'll go ahead and turn off this video, make it a little more comfortable for myself. And during this lecture, this first lecture of this general chemistry sequence, we'll be covering chapter 1. Now, chapter 1 covers the topics of matter, classification, how to make measurements, and the rules that follow making measurements precisely and accurately, and problem solving. I'll be breaking down this entire chapter in shorter, small videos. I hope you appreciate that. But let's go ahead and get started. So chemistry, typically when people think of chemistry, they think it's the study of matter, and that's true. It's a little more nuanced than that. It's the study of matter and the physical and chemical changes that are occurring in matter, and we make observations from these physical and chemical changes so that we can learn about matter. But basically, virtually everything around you is composed of chemicals. So that's why chemistry is such an important course. These chemicals make up matter, and typically when there are physical and chemical changes, associated with those changes are changes in energy as well. Now, we'll talk about the law of conservation of energy, but chemistry is not just the study of matter, it's also the study of energy as well. And we'll get to that in later chapters. So matter is defined as anything that occupies space and has mass. So what takes up space? What has mass? What is matter? Well, the simplest type of matter would be atoms, which we'll get into atomic structure in later chapters. Again, this is chapter 1. It's kind of an introduction. In chapter 2, we'll go in greater detail. When we get to chapter 8 and we talk about quantum mechanics, we'll get in much greater detail as well. But for now, atoms are some microscopic particles that are basically the building blocks. In many cases, these atoms can bond together to form what are called molecules. So if you have more than one type of atom bound together, that would be referred to as a molecule. And when they bind, they form specific patterns of geometry. And that we'll see later also gives it certain physical and chemical properties as well. To give us a simple breakdown, when we look at atoms, you can look at a periodic table, and the periodic table of elements, you'll notice that there are elemental symbols. So when we think of pure aluminum, because it's a pure substance, we think of aluminum atoms. Now on the periodic table of elements, you'll see Al for aluminum. Basically, an element is the plural to the singular of aluminum atoms. So the atom is singular, the plural is the element. That's why you see Al on the periodic table. Molecules tend to be more than one type of element or one type of atom bound together. So here we see isopropyl alcohol. That has a formula of C3H8O. You're not required to know that at all, not at this point at least, but I'm just showing you that it is a specific number of carbons, hydrogens, and oxygens to make this molecule. Now, typically when we talk about matter, you think of, well, how do we see it? How does it occupy space? And it typically occupies it in 3 different states: solids, liquids, and gases. Solids tend to have a more fixed shape of so typically their shape is fixed, their volume is fixed, they're in these geometric arrangements. Liquids have fixed volumes, but they have a little bit of movement. So as a result, their shape can change. So if this was, let's say 16 ounces of water, I could pour that in this tall, thin cup. I can put it in a bowl. It's still going to be 16 ounces, but its shape will change. And then we have gases where we see the majority of space is empty space, and they tend to expand to fit the container themselves. Again, we get in greater details for all of this. This is an introduction for chapter 1. So again, solids are atoms that are packed close together in fixed locations. Typically, solids have higher densities as a result. Liquids are close, but they have what are called modes of freedom. So they can slip and slide. That's why they're viscous, or that's why you can pour them, and they move around each other. Gases, they're far apart. They're flying at high speeds. We'll talk about that with the kinetic molecular theory when we discuss gases. And there's relatively not sticking together, and that is why they do not have a fixed volume like solids and liquids, which are sometimes referred to as condensed states. The state of matter changes from a solid to a liquid to a gas if I heat it up. So everyone's aware of, I have liquid water and I add heat, it will boil off to water vapor. I do want to mention that there are two types of solids. The most common is the crystalline solid that has a fixed pattern that repeats. So when you think of quartz, like salt crystals or diamonds, these have these fixed patterns. There are amorphous solids. In this case, there's a little more flexibility. They do have some order, but it's not long range, so it's a little more flexible. So you think about rubber, plastic, so your milk plastic gallon jugs, or your water bottles, or rubber like in a tire or in a football. Those are considered amorphous solids, and they have a little more flexibility because they're not as fixed. So we talked about matter in the three different states, but we should also identify the difference between what is considered pure and what is considered a mixture, okay? So a pure substance is typically composed of only one type of atom or molecule. It has a fixed composition. A mixture is going to be composed of two or more different types of atoms or molecules in variable proportions. Now, what do I mean by that? Salt water. So salt water can have variable proportions. I could have 5% salt water or salt in the water, 10%, 15%, and so on and so on. So I can increase the salt concentration because the salt's not actually bound to the water molecules like we see in pure substances. However, we'll see that sodium chloride always has the ratio of one sodium ion to one chloride, and water is always, as we know, 2 hydrogens to 1 oxygen in H2O. Again, mixtures don't have these fixed ratios. So again, a pure substance can't be broken down into simpler substances, okay? So here's an example of a helium atom. So when I think of a helium balloon, all the particles in there are the atoms of helium. And if you look at your periodic table of elements, it has He. He for helium is basically the plural to the singular of a helium atom. Compounds, well, what we'll see is that most elements are trying to stabilize and be like what is referred to as a noble gas. So as a result, they're pretty reactive. And compounds are generally more abundant and more common than pure elements because the elements combine with other elements to stabilize and form these compounds. You can think of a compound as the plural to the singular molecule. So here we see a water molecule, H2O, right? So I'm just showing the bench shape. The oxygen is in the red, the two hydrogens are in the white, and each of those are individual molecules. When we look at the plural of that singular, we have water, which we call a compound. It's a covalent compound, and we'll get into that later as well. But for now, we know that a compound has a fixed ratio. So again, H2O is a fixed ratio, two hydrogens to one oxygen, of one or two or more types of elements. Now, when we think of mixtures, when we think of matter, is the most abundant. Okay, so most matter consists of mixtures, and they're different substances, pure substances, just mixed together. So an example is a heterogeneous mixture. So a heterogeneous mixture is where I have a varied composition. I typically tell people you'll have distinct layers. You can see some type of interface separating the two different compounds. Homogeneous is a little more difficult because it's uniform throughout. There's no distinct layer difference. And in the two examples I have here with air and seawater, these would typically be considered homogeneous. Now, someone could argue with the air right now in the cloud formation, which has a large concentration of water, it's slightly heterogeneous. Or, for example, when you drive to a really busy city that has a lot of traffic and pollution, and you see that pollution, that would kind of be an example where air would be heterogeneous. But for the most part, we're going to say air is homogeneous and clear. So again, when we're classifying matter, right, matter is anything that takes up space and has volume. Really, there's two camps. There's the pure substances, which you cannot really physically break these down into simpler things, okay? We'll talk about, why I'm saying physically in a second. Mixtures are more than one pure substance combined in varying ratios, and you can separate them through physical means. So what do I mean? In one example earlier, we talked about salt water. So with salt water, we know that water has a lower boiling point than salt. I could easily separate the water in this mixture by taking advantage that water has a lower boiling point, boil the water off, and catch it. That would be a separation of the two compounds, the pure substances, by physical means. What's in another example? Trail mix. Trail mix is a heterogeneous mixture. It's not uniform, but I could easily separate, for example, the M&Ms from the nuts and raisins by just picking them out. So even though it's a heterogeneous mixture, I can still separate things by physical means. Now, with pure substances, I cannot separate them by physical means. So example, we have elements. In this example, this is copper. So copper, Cu, I'll talk about why it's Cu instead of Co later. But copper as an element is just one type of atom. It's just a bunch of copper atoms, plural. Then we have compounds. So in this compound, this is sucrose. Again, you don't need to know this formula. It's just so you know, C12H22O11. But what I notice with this compound is I have a fixed ratio of carbons, hydrogens, and oxygens to one another. And it creates this entire molecule. A molecule is a singular to the compound, to the plural of the compound. So if I go to try to separate compounds physically, I can't do it. So I'll go back to H2O. H2O is an example of a compound. If I try to physically separate the hydrogen and the oxygen by boiling it through physical means, I can't do it. It's going to boil off as water vapor. It will only change the state from liquid to gas. So I can alter compounds through not physical means, but chemical reactions. So we will talk about that. And I can break bonds and have chemical reactions of compounds to change what they are. But for the most part, when we think of pure substances, they have fixed ratios. They cannot be separated physically. And basically the difference between an element and a compound, an element is one type of atom. A compound is more than one type of atom chemically combined. Homogeneous mixtures are uniform throughout. So if I look at this T, it's the same color throughout. There's no layer difference. However, why is it considered a mixture? I have more than one type of compound. I have water. I have some sucrose. I have some caffeine. Why is it not considered a fixed ratio? Well, I could always add more sugar and have a variable mixture. It would still be T. It would still be homogeneous. I come over here to heterogeneous. What do I notice? Two distinct layer differences. Here I have oil and water. They separate. Why? Oil is nonpolar, doesn't mix with water, which is polar. We'll talk about that later as well. And we can see this distinct interface right here. It's still a mixture because it's two things that are combined in variable proportions, but it has a distinct layer difference. You can think of oil and vinegar, for salad dressing as well. That's why you got to shake it up. So I just want to make sure you're comfortable with these topics. And I always do quick checks. We'll also see that we have worksheets that I want you to print out and have available to answer the questions during these lectures. But I typically tell students, you can pause right now and try to answer these questions before I show you the answer. Do them on your own, and then turn the recording back on and see if you got it correct. So for this quick check, I want to classify the following as a pure substance or a mixture. Once I know what it is, if it's a pure substance, is it an element or a compound? If it's a mixture, is it heterogeneous or homogeneous? So seawater, it's a homogeneous mixture. It's got salt, it's got water. Now again, people could be sticklers and argue, well, what if there's a lot of kelp or algae? In that case, again, in general, salt water is pretty uniform, okay? So we go to sugar. We had that earlier on the slide. It is a compound. Why? It has that formula that we talked about earlier, C12H22O11. And it has a fixed ratio. Mercury in a thermometer. Now, you can look on a periodic table of elements and you'll see mercury has the elemental symbol Hg. Again, we'll talk about that later, but for now, that is the symbol for mercury. And that's because it's a pure substance and it's an element. And again, the singular of the element is an atom. The singular of a compound is a molecule. What about chicken noodle soup? Well, that's a mixture. It's heterogeneous. You might have the noodles, on one side and the little chicken pieces on the other. Okay, so it's not evenly distributed always. And it could have variable proportions depending on how much chicken is added. Okay, that's great. So that is kind of a discussion of matter and how we categorize it at pure substances and mixtures, and how we break pure substances down into elements and compounds, and mixtures into homogeneous and heterogeneous. But I did say in the introduction that chemistry is not just the study of matter, but it's also the study of physical and chemical changes that occur with matter, and also the energy that accompanies that. So now we're going to look at some physical and chemical properties so that we know how to identify them. A physical property is one that can be displayed without changing the composition of an element or a compound. Okay, so what's an example of a physical property? Maybe color, maybe shape, right? Texture, right? These are all examples of physical properties, okay? What are chemical properties? Well, maybe it's corrosive, flammable, right? Those are examples. So with physical properties, again, odor, color, texture, some of the physical properties I want students to really be aware of are melting points and boiling points, right? So we said earlier, if I boil water, so here I have liquid water, it's a condensed phase. What does that mean? It means the molecules are close together and sticking to each other, right? It has a fixed volume. They're moving around and slipping and sliding. They're not in really strict geometric patterns like solids. So they take the shape of the container, but the volume's fixed because they're condensed and they're sticking together. Well, when I heat this up, it boils, and now it forms a gas, and the particles aren't close, so they're not sticking. So now when they don't stick, they don't have a fixed volume, and they can, fly at high speeds, especially in an open container, and fly out. That's actually called vapor pressure. So melting point and boiling point are really important properties. One of the compounds, one of the pure substances you should be comfortable is for water, the normal melting point, so that's at 1 atmosphere, is 0 degrees Celsius, and the boiling point is at 100 degrees Celsius. So typically water is kind of the reference point for all our compounds, even when we compare mixtures. So the one you should be familiar with, no other ones, but for the melting point, boiling point is that of water. So normal boiling point, 100 degrees Celsius, normal melting point, 0 degrees Celsius. You should also know that density is, and we'll get into that, mass over volume, and it's how closely packed the water molecules are. Water is typically the one density of all of these compounds you should know. It's really easy because it's the only one. It's 1 gram per 1 mil. So the density of water is 1 gram per mil. Now, chemical properties are a little bit different. There is a change in the composition. Unlike physical, again, if I go back, if I boil this water, still water molecules, it just went from a liquid phase to a gas phase. Okay, that's a physical change. I boiled it. Chemical property, there's actually a chemical change. So I'm going from pure iron, okay, and we'll do balancing of equations later, which is a solid, right? And this is an element. The singular are the iron atoms. So every single one of these is an iron atom. That's the singular. The plural of all of them is iron as the element. But if I expose this to oxygen, we'll talk about oxygen being a diatomic. So what do I mean by diatomic? 2 oxygens are bound together. They're chemically bound. It makes them more stable, all right? But this is still considered an element because it's only one type of atom. But you take oxygen and iron, right? And over time, they're going to produce what's called iron 3 oxide. Now, again, we're not into nomenclature, but what we're seeing is we're seeing a change in composition. This is a chemical property, iron rust. And if it's in the presence of oxygen, your iron 3 forms, the iron is a positive 3 charge. The oxygen becomes a negative 2 charge. I take those superscripts, I make them subscripts, and I get the formula iron 3 oxide, which is a solid. And that's what we see here as rust, okay? And that's a compound. So that's a chemical reaction. We'll talk about, nomenclature and determining formulas and charges in chapter 3. When we get to chapter 4 and 5, we'll talk about reactions and balancing this equation as well. It's very simple to balance this equation. This will be a 3, a 2, and a 4. But again, that's a different lecture. So now covering these topics, I want to make sure that you're fairly comfortable. So when you look at this, is this a physical change or is there some type of chemical change here, right? Or a physical property? Hydrogen, it explodes, right? So typically with explosions, there's a large amount of energy, right? And why is that? Well, typically there's a chemical change in that process, an explosion. So you change the substances. So that means that for hydrogen glass to be explosive, that must be a chemical property. Silver is shiny. Okay. We're not talking about it reacting. We're just discussing a physical appearance, right? Kind of like its texture being smooth or its color being gray. It's shiny. It's reflective. That's physical property. Dry ice sublimes. Now, sublimation is when a solid goes straight to a gas. And we see this, well, we actually see the opposite of this. We see water and freezer burn in a freezer. So water vapor solidifies. It's called deposition. And that's why you get freezer burn in your fridge. Well, that's deposition. Sublimation is going from a solid to a gas. Where do you see that? Dry ice. What's dry ice? CO2. So if you ever buy like a ice cream cake and you go to Baskin Robbins or something, they give you that little piece, that white piece that looks like ice. That's CO2. Okay, but it sublimes, and when it vaporizes, it stays as CO2. So that's simply a physical change. The air temperature warms it up, separates the CO2 molecules that are in a fixed pattern, gives them space, and then they vaporize. All right, D. Copper turns green. All right, we haven't talked about this, but anytime there's a color change, I know we said color is a physical property, right? So we said that earlier. However, if there's a change in color, that usually means a reaction occurred, okay? So if copper turns green when exposed to air, like we see this, the Statue of Liberty, it's green. It wasn't always green, right? It was copper. Why? It oxidized. That's a chemical change. Okay, so it produced copper 2 oxide. All right. So now that we've identified physical properties, again, color, texture, melting point, boiling point, density, it doesn't change the composition. It's just describing its state. Chemical properties, corrosive, explosive, flammable, can conduct, rust, those are all chemical. Now we describe changes. So a physical change, it might change its appearance, but it's still the same compound or substance. So we use boiling, right? That was a physical change. Boiling water. Another, if I take a piece of paper and I rip it, right? So I take a piece of paper and I rip it. Still paper. I just ripped it, right? I changed its shape. That's it. And maybe its physical appearance. Or like if you get a piece of tinfoil and you squish it in a ball, still tinfoil, right? You haven't changed the composition, just its shape. That's physical change. Well, what about a chemical change? Well, that's different. Now I'm changing composition, right? So it's no longer the same thing, okay? That's when we need to write out reactions. And what you start with is the reactant. And the reactant is the starting material. That's what you start with. You break bonds in these reactants. You form new bonds. So typically with reactants, you break bonds. And then you form new bonds. So you're shuffling these atoms around, and then you have what you end with, because you have new bonds forming. You call that products, because that's what you produce, okay? So what's an example of that? Well, if I take that same piece of paper earlier that I had squished up or ripped, what if I light it on fire? Does it stay paper? No. It turns to CO2, all right, and water vapor, gas, and you might have some ash left over, some carbon left over. And what else does it do? That chemical change, when there's a chemical change, a lot of times we'll see a change in energy, right? So I'll draw a little triangle. Triangle means change. So a lot of times with a chemical change, it's accompanied with change in energy. I mean, after all, isn't that why we burn gasoline?
right? We're not burning gasoline because we want to produce CO2 and H2O in the atmosphere. We're doing it because we need the energy to drive our machines, make our roads, move our cars, build our skyscrapers. All right, let's see how we're doing. So, can we categorize these as either a physical or a chemical change? Copper metal forms a blue solution when dropped in nitric acid. You're actually going to do this in one of your experiments. They change the numbers every semester. It's called the copper cycle, and we'll be doing this. And it's the first chemical reaction in the copper cycle experiment. Okay, we conduct 5 reactions, and we take a copper wire, change its composition through 5 different reactions, and then bring it all the way back to copper again. It's an awesome lab. So hang in there. Okay, B, a train flattening a penny. So let's say you go and take your penny and you put it on a railroad track. I used to do this as a kid. You put it on a railroad track. Now don't do that, by the way. I was not the smartest thing. But you put it on the railroad track. The train comes, runs over it. When you grab it, it's still a penny, right? But now it's all flat. Just change its appearance. Just physical change, still a penny, just flat. All right, what about, we just had the 4th of July, a match igniting a firework. It's a chemical change. What do you see, right? Energy change, heat's given off, light. Those are all forms of energy, right? Ice melting. Again, ice, solid water is ice. When it melts, it's just liquid water, a puddle. It's physical. All right, so moving right along, and again, for a lot of you, this is a review. So when you look at this, right, up to this point, we introduced matter, right? We basically said chemistry is the study of matter and the physical and chemical changes that are accompanied with it, along with energy changes. And we classified matter into the 2 camps, and then we classified physical and chemical changes. Well, how do we even notice any of this? Like, how do we notice matter and, these physical and chemical changes? Well, we use a scientific method. So typically what we do is we use observations, and based on observations, we design experiments to help us understand what the heck's going on, right? So Aristotle, right, used the same logic. Now, he was a philosopher, so philosophers are a little bit different than scientists. They use a scientific method approach, and they came up with, conclusions, theories and hypotheses and law, they use logic, reasoning, and debate. Now, scientists were a little bit more empirical, right? So we're going to use empirical formula or empirical evidence, and that's why we need to take measurements. That's why we need to understand numbers. We use numbers and physical and chemical changes to back up our theories. So typically, what are the steps of the scientific method? Whether you're a philosopher, right, or a scientist, because they're pretty much the same. You're seeking truth. You're trying to understand. But one thing is you're going to question something you observe in nature. Maybe when you observe something, you might try to explain it, right? So you construct a hypothesis. And then, maybe you're so bold and you become a scientist instead of a philosopher just talking about, your conclusion or your hypothesis. You actually design an experiment to test it. And then once you test your hypothesis, you collect data. And again, your data could be qualitative or quantitative, but you're going to collect your data. And then from your data, you're going to analyze them. We call those results. You might analyze them using graphs. You might use calculations, right? You might use different types of relationships, but you're going to try to analyze these and explain your observations in the experiment from the data you collected. And then to see if it supports your original hypothesis, and then you're going to draw conclusions from that. So you might realize in your experiments, these conclusions do not support your hypothesis at all. And now what do you need to do? because of these new conclusions, you need to design a new experiment, right? And not only do you need to design a new experiment, you might need to come with an alternative hypothesis. In fact, some of you may, if you've taken biology or genetics, there's something called a null hypothesis. So typically one experiment cannot prove, right, beyond a reasonable doubt, a hypothesis. It's not conclusive. One experiment isn't enough. You need other people to be able to do the same experiment. You need different experiments to help support your theory, okay? So it's very difficult to prove your hypothesis. It's a lot easier to disprove it. So a lot of times what people do is they create a null hypothesis so that you can disprove that and support your hypothesis, okay? But we'll get into that later. Again, these steps for the scientific method, they do not have to be linear, okay? They do not, even though this looks linear. So a lot of people are like, this is a lot of information. I get it, right? But you are a scientist now, and you're going to be approaching everything with this type of format and discipline. And I know what you're thinking, how am I going to do this? You already do this. You already do this, right? You try to explain things. We're just going to be doing it in lab through experimentation. Now, what about theories? Well, those are very well-established hypotheses. And, we're going to try to support some theories in lab and see if all the students, right, come up with the same results. That supports the theories and the phenomenon that we see, right? That's evidence. And it's considerable if everybody's getting it right. That'll support the theory. Well, what about laws? Laws are a little bit easier. They're not as difficult to prove. They're just kind of obvious. Like there's typically no condition. So an example of law, like the law of gravity, right? If I take a pen, right, and I hold it up and I let go, it's going to drop. That I don't need to prove that. Everybody's seen that, right? There's no exception to it, right? So that's a law, right? So what might be a theory? A theory might be evolution, right? Right. It's not conclusive just based on one thing. You piece things together, right? Like homologous structures, fossil records, artifacts, scrolls. You can piece things together, right? That's a theory. But as the great man said, Albert Einstein, no amount of experimentation can ever prove me right, right? But a single experiment can prove me wrong. That's what I was saying earlier. One experiment is not conclusive. It supports what you're trying to prove in your hypothesis, but it's not conclusive. However, one experiment can kind of prove that null hypothesis that I was talking about earlier incorrect. A lot of information, I apologize, I know, but you can remember it. And you're probably thinking, oh, heck, how am I going to remember all this? Well, you just said it. You're going to use the acronym OHEC. OHEC is the scientific method. And you're just going to apply this discipline, which you've already been doing, but now you're just going to use this acronym to remember. So what do I mean? O, right? Observations. You already do that. Now we're going to do it in lab. The experiment's been designed, so there's already going to be a hypothesis, but out in nature, you might be looking at things and draw your hypotheses. And now what are you going to do? Well, you can't just from your hypothesis. I mean, I guess you could debate, right? And use logic reasoning and say your hypothesis is conclusive. And that's what philosophers do. That's great. You can get stuck in that rhetoric, though. So what's a better thing? Design an experiment, right? Get physical, chemical data, empirical evidence, right? Use numbers. It's a lot harder to argue. Numbers are not subjective, okay, like opinions. They're not subjective. They're objective. You can't argue the number, okay? So get your experiment, and then you're going to collect your data. So remember, experiment is to collect data. And there are two types of data, right? There's qualitative So qualitative, that might be like a color change. I take two clear solutions, I combine them, and there's a color change, there's a precipitate. So that is evidence that a reaction occurred. Okay, that's qualitative. Now, quantitative is what we focus on, because we're scientists and we're physical science, we're chemists. So quantitative data might be, well, I want to know how much of that precipitate I formed. So I might take a filtration apparatus or filter paper and get a funnel and decant, the liquid to separate it from the solid and pour it in there and separate it, right? And then I might take a mass measurement. And that mass measurement might give me a certain amount of grams. Maybe it's 18 grams. Well, now that's quantitative. And I can't deny that. I have 18 grams of a solid. So once I collect my data, I got to analyze it, and I get two types of conclusions. And again, what, right? So the two conclusions are what will happen. Those are laws. Those are a little bit easier. The conclusions, they're kind of like pattern recognition. Like going back to the law of gravity, I know if I let go of a pen, it's going to drop. So I can draw a conclusion from my experiments that, okay, this is what's going to happen based on what I've observed, right? What's a little more tricky is why. The why is the theories. Well, why is this occurring? Why is this dropping? Is it a gravitational attraction between two objects? Is it dependent on their masses? Who's pulling it from what? Okay, because really gravity is a theory. Okay, I hope that helps. That is our first video. Our lectures are going to be an hour and 20 minutes, but I don't want to make hour and 20-minute videos. So I'm going to stop right there. This is a good stopping point, and I'll start up the next video, and I hope you enjoyed it.